Hello everybody, my name is Ondřej Fikar and I will give a talk about machine learning and cybersecurity and threat detection, as you can see on the slide. I've got some 20 minutes and the topic is quite complicated and it's a lot of things to say, so it will be very, very lightweight. And if there is something you are interested in, don't hesitate to ask me during the presentation or later in the pub. I will start with the introduction to cybersecurity. Then I will say something about machine learning in the domain. Then I will give a brief description of Tor, and then I will describe how we can detect it. So, first part, cybersecurity. Why should we even bother about cybersecurity? Well, the simple answer is because the computers are everywhere and we depend on them. If there is something wrong with our computers, we usually lose a lot of money and sometimes even lives can be in danger. So that's why the topic is important. Here are some examples of the malicious activity we encounter in the internet. It's like sending spam, denial of service attacks, information theft, password crackings, and the list goes on. I guess you can find some other examples. The important thing here is money, because all the activities which were on the list can bring you a significant amount of money, and it means that the cyber criminals are well organized and well funded. The myth about hackers doing their jobs in basements and basically being geeks and students, it's not true anymore. Today it's organized crime, and it's domain of large groups and sometimes even national states. Now, more technically, how do the cyber criminals do it? Well, it starts with an infection. Like you receive an email with an attachment which is executable, saying that someone loves you or something like this. You click it and boom, your computer is owned by someone else. From now on, the new owner of the computer, the black hat hacker, can do whatever he wants with the computer, and usually the infected machines joins large network which is called a botnet. A botnet is a group of infected computers which send spam, perform the attacks, and do all the nasty stuff. You can think about it as it's some kind of cloud, very cheap because you run on computers which you don't have to pay, and if they are broken you just get some other computers. But the important thing about botnets is that they have to communicate. Like, in order to send spam, they have to send emails. In order to crack password, it's necessary to download the passwords to them and to get the correct passwords back. This is really important for the machine learning part. So try to remember that. Now, why machine learning? The thing is that the computer systems grows in volume and in complexity and quite steadily, and it will be even worse because the Internet of Things is coming, and when it's here, like basically every device will be connected to the network, which is like, from the security point of view, it's a disaster. And today we lack some millions of security professionals worldwide, and as I said, it will be worse. So the answer for this is automation, as usual. So how can we automate cybersecurity? First thing, antivirus software. Like everybody of you has an antivirus in his or her computer, at least I hope. But it's not enough. First of all, for antivirus to detect a threat, the threat has to be known. It means if there is a 0 day, you are not protected. Also, the antivirus software usually runs on the machine, and you cannot, like, when there is a malware running on your machine, it won't help that you have also antivirus running on the same machine, because the malware can alter the antivirus software as well. So we can use traffic analysis, which is what I did. It can be rule-based. So you design some rules. Think about like firewall rules, which prevent performing some kind of actions on the internet, or when there is some malicious action going on, you can like an alarm can be made. It's better than antivirus. I mean, it's different and it can help sometimes, but also the rules are designed by humans. So the same problem with lacking professionals is here. Or we can learn the rules. We can learn what is a normal traffic on the network, and if there is something anomalous, the system can react automatically. Now I want to give example of concrete application for threat detection, so you can get some idea how it works. So I'll start with description of Tor. As you may know, it's a tool which lets you browse anonymously. That's cool, and it's good to have such tools, and it's totally legitimate to run Tor as a private person. But unfortunately, if it's run in a corporate environment, usually it means there's some data breach. Also, there exists malware which uses Tor as its signaling channels. And the reason for me to try to detect Tor is that if I'm able to detect this kind of communication, I might be able to detect some other kind of communication as well. For example, malicious software, or the communication induced by the malicious software. And just a little note, by identifying users which use Tor, we don't compromise the anonymity of the users, as it is defined by Tor design. Because the reason of Tor is to hide what you are doing on the internet, not that you are doing something. So how Tor works. Without Tor, if you want to get something from the server, you just send some packets to the server and you get your reply. Along the way, if anyone taps the network anywhere, he knows what you are saying, what you are sending, and where. If you use some kind of encryption, he doesn't know what you are sending, but he knows that it goes here, and if he knows what's the purpose of the server, he knows what you do anyway. That's the metadata thing. So Tor solves this by placing other computers along the way. Those are computers run by volunteers, and usually they are called relays or routers. So you send your message to one, then it's sent to another, and then it goes to the server. If someone taps the network here, he knows that it goes somewhere, but it's just some computer out there, and he doesn't know the destination. If someone taps the network here, he knows that something's going on, but he doesn't know it's you. To prevent traffic analysis, Tor use like more chains of the computers at the same time, or it switches them through the course of time. This is also important for the later things I will say. And if we monitor the network where this computer is, we usually see just this. So we don't know what's happening out there. Now, how do we find that someone is using Tor? First thing for machine learning is data. So the data we have here are NetFlow captures, which are basically some summaries of communication of the computers inside the network. In a NetFlow we have information like source and destination IP, port numbers, protocol, time, but you don't know the content of the communication. First, you can't store it because it would be too much data. Second, it wouldn't be really ethical to store it and examine it. So that's all you have, and you have to go with this. From the Tor specification, we know that it switches to this line over here. It's called circuit, and Tor switches circuit every few minutes. So the idea was to examine the timing patterns of Tor. So we made a histogram for each server or computer in the network. We made a histogram of duration of flows going to it, and we used this bins of the histogram as our features. And we found out that this is a histogram of a usual server, like thinking about HTTP server or something like this. And you can see it's a mixture of some distributions. Here, this is roughly exponential. Then there is some spike. This is because of some protocol which is used by the server, and that's it. This is a histogram for a Tor computer or Tor host, and you can see there is a huge spike over here. This is some 3 minutes, and it's exactly the time specified by the protocol. And there's not the exponential part here. Great. The problem is that there are also Tor hosts like this, which behave like completely different. And if we train some, let's say, standard classifier, such as SVM, with these features, we got these results, which are not really satisfactory. And so we tried other features, none of them helped. Like we tried everything from this list and some combinations, functions, whatever, nothing worked. Then there was the idea that the users, or not the users, but the computers which participate in Tor has to communicate with the routers. There is a finite number of the routers, and we expected that they don't do anything else. So in theory, there could be some kind of, like, if there is another computer here participating in Tor, there is chance that it will communicate with the same router as this computer here. So we defined something which we called mutual communication graph. Here's an illustration. The big red points are servers and the blue ones are users. And we expected, yes, and there's a little trick in here, it's inverted. So we expected the servers of the same purpose to have the similar sets of users. And because we didn't want to work with a bipartite graph like this, we defined an condensation. There are only servers and the links between them are weighted according to the number of the common users. So A and B share a lot of users, so there's a strong link. I didn't have any equations so far, so here are some formal definitions, but they are not really important. What is important is what you get when you try to build such a graph from the real traffic. This is a snapshot from a company for some 2 weeks, and all the dots are the computers outside the company's network, which are contacted from inside the network. And you can see that indeed there are some groups like this one, this one, this one. And what's the best thing about it? The red dots are the Tor routers and they are clustered together. So it seems it works. So the last thing to do is to perform some kind of clustering analysis, and you get something like this. This red cluster over here is the Tor cluster. Unfortunately, there is something appended to it. But if you make the number of clusters higher, like some 450, which unfortunately I couldn't visualize, you get this part here separated. Now you get clusters, but you don't know which one is Tor. So you get back to the initial SVM and you make the histograms not for one particular computers, but for each cluster. And if you classify the clusters like this, you get a way better result. It's not perfect. Still, we get only 60% of Tor routers and miss some 40% of them. But the precision, this means the number of true positives in the returned data is 96%, which is great because you can use this for real-world application. Like, you don't want a network administrator to deal with data where there is some 50% of false positives. But if you have 96% of true positives, you can work with this. So that's it. So to give some conclusion, cybersecurity is important, obviously. Machine learning can help, and from my point of view, it's the only solution for the cybersecurity problems which we face today. And there's a lot of research going on in the security. And yes.
Sorry to interrupt you, but if I remember correctly, I tried for several years earlier, and it was really slow. So I'm not sure how often it's used by internet networks for transferring the data and so on, because I'm not sure if it's reliable enough.
It is used. It's not the most common way to do it, but it's used. The thing is that it's not only malware. As I said, it could be like individuals in companies, which is something which bothers them. I mean, the companies. They are afraid of their data being stolen, so they want some kind of protection against this. And also, the Tor communication is kind of similar with the malware. It's kind of like Tor communication is kind of similar to the malware communication, in the sense that usually Tor contacts a lot of servers or routers outside, and if you have a peer-to-peer based malware CNC channel, it looks kind of the same. It's not the same, but it's very difficult to get data for malware, and it's even more difficult to run it in a lab. But you can run Tor. So if you design an algorithm for Tor, you can then use it for malware with some slight changes, and you can hope that you will get some reasonable results. And this is a work in progress.